welcome to another video. Today we have got day 11 finally of 30 days of machine learning. So this is a continuation series for 30 models, all separate, built on amazing problem statements which we analyze in depth from scratch. Let's start with the problem that we have on day 11, mall customer segmentation. Okay. So first of all, the title itself sounds a bit complicated, so I'll start with explaining that. Small customer, mall customers, okay, the customers who visit the mall. Segmentation means grouping. Segmentation means grouping. It means, placing people into groups. So in this case, like placing customers into groups. So we'll understand why we are doing that. First of all, let's look at the problem statement. So we have got the mall customer dataset from Kaggle. I will attach the link to the dataset and you can look at it. So, we have got basically mall customers who visit the mall for shopping and we have certain data about them. And our goal is to discover some latent customer segments in the feature space without any supervision signal. So this is something worth explaining. So let me quickly get on to it. Okay. So, whenever we talk about, any machine learning algorithms, what we get on our hands is that this is, ML. We get supervised machine learning and we get unsupervised machine learning. Okay. So what happens is that in supervised machine learning, we already have predefined labels available with us, which means that, like in all the problems that we had till now. Okay, so both classification and regression problems, we had some sort of a target variable available with us, where we just had to use the historical data and analyze new trends to predict the target variable again. So let's say something like a maybe like a linear regression problem. So if you have something like this, and your goal in linear regression is nothing but to find the best fit line. So let's say the best fit line is like this, like a linear line, a straight line. So in this you have this target variable specified. It can be anything. Let's say it's a customer churn problem. Okay, so either the customer will churn or it will not churn. Okay, or maybe it's like a height weight problem. Okay, let's say that let me erase this quickly. Let's say that I have, I already have, let me choose this one. Okay. So let's say that X represents the weight of students and Y represents the height. Okay. So I have the weights of students in the form of a historical data set where, I have a data set like this. Okay. So some values of weights are available, some values of height are available, and I have to use this this historical data in order to predict new values of height. Okay. So in this problem specifically, the label is going to be height because this is the one that we are predicting. Okay. Now, for unsupervised machine learning, what happens is that there are no labels available. So, what's the problem? If there are no labels, then what is the problem that we are solving? So, for example, imagine we have such a data set. We have got customers, okay, like we have this time, we have got mall customers. We have got their annual income, and we have got whatever money they spend, their spending score every day. Okay. And what they basically want us to do is that they are saying that there are no true labels in the data. So you should go and find them. They are basically saying that, go into the data and discover some patterns in the data, some structure in the data. That is the ultimate goal of unsupervised machine learning. So, if I write it down, so our goal basically becomes to find structure in the data. Okay. Structure in data. You can also say patterns, pre-existing patterns, but structure is like a more suitable word in the context of what we are talking about. So, basically in this case, that is exactly what we are going to do. So we have the annual income and the spending scores of the customers who are visiting the mall for the shopping or whatever. and we are supposed to use that and basically cluster them in different groups. How will we do that? How does it all happen? I'll discuss this. First of all, let's get on with our usual pipeline that we do. So for that, I say we go on back to the repo. Okay. So first of all, I wanted to discuss this. You can read this as well alongside. This is like the business problem part of it. Like, why are we segmenting the customers? Okay. So, like, if we are predicting the weather, if we are predicting customer churn, or we are solving any other machine learning problem statement, it makes some sense, right? That what value is it contributing? Customer churn will tell us whether the customer is going to leave the service, specifically the telecom service or not. So, basically it is to prevent any future business loss. Okay. Any monetary or financial risk that is to the business. So what profit does or what advantage does this segmentation process bring to us? So you can read it as well. It's pretty easy to understand. So, in malls, there are marketing campaigns which are basically run according to the groups of customers. So, let's say that we have got a group of customers like this. These X points represent the customers who like to shop expensive. They don't care about what money they're spending. They just want to get the good brands. So, all of the expensive brands, all of the top end brands. So there's a group of customers. So the top end brands are aiming to please or bring these customers in as much as possible for the shopping. So their marketing campaigns will be addressed to this group of customers. Okay. Then there are customers who only go for optimization. It means that they are not in there to spend their money. Let's say that these red dots represent those groups of customers. Okay, they are the ones who are looking for deals, looking for sales. So let's say that there are good brands out there, maybe like Max or maybe like some other shopping stores, maybe clothing shopping stores which offer some deals, maybe like something like a 30% off or one-on-one deal where it's like if you buy one you can get another free with some constraint in it. So those types of brands will be targeting these group of customers. And if they were all mixed up together, okay, if let me open this up. So if I had these customers mixed up, okay, if I had them, mixed up like this, okay, so some of them are these customers who are in for the sale and in for the deals, and then I've got these customers who are in for the top end brands. Now the marketing campaign cannot be done very smoothly because the stores who are targeting these customers don't really know clearly as to who their customers are. So, separating them into different blobs, different structures, different clusters is very, very advantageous to the businesses themselves. Okay. Then you can read the other ones as well. They're pretty easy to understand. So, model customer lifetime value per cluster. So this is also very important. So once we have separate segments with us, the business that we are talking about, the business in question here, can identify a lifetime customer. Okay. And it can also get a value as to what profit each customer can bring in to the business. Okay. So this is also a very intuitive point that they can maybe make loyalty programs for high income, low spend customers. Okay. So like let's say that there's a high income customer who always comes to the same store to buy the same thing. So maybe they can like let out a lifetime card or something like those sorts of loyalty programs. Like in McDonald's, they have got the golden card, which is very rare to get your hands on. So if you get that, you can eat at any McDonald's for free. So these sorts of things. Now they don't give those cards out like this. So for that, if they can segment their top priority customers, the richest customers, the most influential customers, their job will become far easier. Okay. So this is the point. Our goal is to find some structure in all the chaos, find some patterns in all the chaos and keep them separate for eventual business profit. Okay. Moving on to the pipeline, it's the typical pipeline that we implement. Nothing fancy, nothing new. Okay, we always start with understanding the data, which is always done through the EDA. It is always for the engineer. Okay, so here the EDA is done primarily in four steps, and I'll be showing you that. Okay, it's pretty important to understand the EDA because the model that we are going to use today becomes very intuitive once you look at the EDA. Okay, so when I open the EDA, okay, this first of all we have on our hands a scatter plot between the spending score and the annual income of the customers. Okay, so if I show this to you in the code is like 2 lines for this. This is how you can code it up. Okay, I've commented the code out because the EDA does not contribute to model training, and later I trained the model in this code itself, so I commented this out. Okay, so what we did was we basically plotted this, the annual income and the spending score between 1 and 100. This is the title, and then we basically showed the plot. This is using Seaborn library. This is basic syntax. Now back to discussing what it is giving us. So can you observe something in this data set? Is there some pattern already visible? Yes, there is. So if I copy this, maybe if I just a second, let me copy this image, copy image. Let me open it somewhere else so that I can show it to you, you know, what we are dealing with. So let me copy this right here. Paste. Okay. So now let's discuss this specific picture, why it is so good. So what do you see in this scatter plot? Do you see some structure or all these random points? No, we definitely see some structure. So if I take my pen and try to make some structure, I can already see some way I can group some of the points together. Okay. So these points are all collective together. So maybe I can group them together, right? I don't know whether it is true or not, but if we are just doing this intuitively, maybe I can group them together. Okay. Then maybe I can group these ones together as well. Okay, and these ones as well. Okay, what about these ones? I can do them as well. And the most obvious, I can do these ones as well. So we can see in the scatter plot itself that the distribution of these points. Now, what are these points? They are not random points. They are the customer spending score and annual income values itself, which are plotted in the form of a scatter plot. So I can already see that these values are not random. There is some structure available, which we can see very intuitively in the scatter plot itself. Okay, we can already see these dense regions. Okay, all of these dense regions or blobs, as we call them, or maybe even can even call them clusters, which is the formal name, by the way. So we can already see these dense regions in the EDA itself. So this already gives us an idea that we can lean towards something like a clustering algorithm. Okay, don't worry, I'll be discussing what happens in the clustering algorithm, but first just try to understand this as to how we decode what model we are using each day. Okay, so this basically this scatter plot here in the EDA, it isn't just for seeing the graph, it isn't just for aesthetics. It basically verifies our intuition that clusters can be formed there, and it verifies that we can and we should definitely think in the direction of a clustering algorithm. Okay. Now, going back to the EDA, let me open this up. Okay. So these are some more important distributions that we see. So, when you can look at this, this is just the histogram of the income distribution. This is the same for the spending score. Now, I'm again going to copy this and show you something in this. Okay. It's very direct to understand, and you will definitely enjoy this. So let me just paste it quickly here. Okay. So let me enlarge this just a second. Yeah. So, I've pasted this here. Now, let me move on. So, what do we observe in this? This is the spending score of various customers, and this is the count on the y-axis right there. Now, look at this very carefully. This bar right here represents a very high value, right? It means that, about 40 customers or more than 40 customers have this 50 spending score. Okay, that's fine. That's okay. But do we see any other value close to this 40? No. The other biggest value is straight at 30. Okay, so this is like the largest value. And this value is the lowest. Okay, this is maybe the average. So there is a massive difference in the distribution of the spending score values. Okay, we can see that we can basically infer from this that the spending score distribution also reveals some sort of a separation that can be made. So this also gives us an intuition that we should definitely be heading towards a clustering algorithm. Because, if the data was like super duper uniform, where all the bars were like, close to each other, it was something like this, then, no external patterns could have been incurred from the data. But this histogram right here, it reveals a lot of difference in the spending score itself, which gives us an idea that, yeah, a clustering type of an approach is actually, we get a confirmation that a clustering type approach is the correct way to go forward with. Okay. So this also geometrically, verifies as to uh, what we want. Also, just remember this, we'll discuss this later, but I just wanted to state this now. You see these regions that we made right here, these clusters, okay, which we call as dense regions. So the thing is that these regions, they should be spherical in shape, or they should be very close to spherical. Those are considered as very good clusters. Weird shaped clusters like ring shaped or crescent shape are usually avoided. So spherical structures, okay, spherical clusters are considered very strong. So, in this, if we intuitively try to get an idea, we are actually getting spherical ones. So, this again gives us another point of confirmation that clustering here is a good choice. Okay. So now moving on from the EDA, okay. Now you can look at more in the EDA itself. If I open it up, you can also analyze this income distribution. This also gives us the same thing. Some values are very high, some are very low, which means there is some underlying pattern that we can use and interpret as a clustering model itself. Okay. Now, very important. K means I am on my way to introduce the algorithm itself and the math from scratch. But first let's just state this. So just like the KNN model, the K means is a distance-based algorithm, meaning that uh, the decisions that we make while running the algorithm are done by calculating the distance. Okay. So wherever the distances are calculated, we need to bring the feature values to a comparable range. Okay. So, this can be seen right here. Let me open the notes again. So, once you look at this spending score, you see how high this value is. Okay. This is so high. This value is very low. Okay, whereas if I open the income distribution has a different scale altogether. There are many values lying close to 30, 35, and 40, and these values are very low. So if I get this income feature and if I get this spending score feature, so their distributions are very different. Okay. It is very much possible that one of them will affect or one of them will hamper the learning of our machine learning algorithm, and the other one not so much. Basically, basically our model will be influenced too much by one feature, especially the feature which has the higher values. Okay. So we need to bring the feature values to a comparable scale. So what do we do for that? We do the typical thing that we have been doing since day one. We do feature scaling using a standard scaler. Let me quickly get back. So, wherever distance-based algorithms are involved or calculation-based algorithms are involved, where, the splits or the decisions are made being based on the distances, we always need to apply this formula to our feature values, all of them. Okay. This is called as the standard scalar step. This is done using standard scalar. Okay. It's the scaling step. This mu is nothing but the mean, and this sigma is nothing but the standard deviation. Okay. Now, this standard deviation is nothing but the square root of variance. Okay, some people understand statistics better in the term of variance. So I just write it that this is nothing but the square root of variance. Okay. Now, whenever we apply this formula to all of the raw feature values, the mean of the entire data set is converted to 0, and the standard deviation is converted to 1. This brings the features to a comparable range. Now, we cannot say that one feature is going to dominate too much. Okay. This is done by the scaling step. Very easy, very intuitive. This is not something new. We have been doing this, but it is pretty important. So, I basically keep mentioning it. Now comes the main problem. Okay, we are going to, you can read this, but it's basically theory. I'll explain it in a much better way. So first of all, let me go back to the code. So look, you can look at the code as well. This is simple. This is how you get the histogram, the his plot. KDE means kernel density estimate. So basically, when you see how we have printed these stacks of data here, and we have got this line showing how close it is to a Gaussian distribution. So the KDE is equal to true enables us to get this line in the plot. Okay. You can remove it as well. It doesn't really matter much. It's just that the EDA was needed to visualize the data and to verify our assumptions. Okay. This is the feature selection. So this is simple. This is the scaling that we have done. Typical, okay, using standard scaler, and the standard scaler we imported right here. Okay. Simple. Then nothing, then we go on to all of the stuff that we have done. Now from here, I say that we close this and we go back to building the algorithm from scratch, understanding as to what happens. Okay. So we have understood that till now that the EDA is saying, and it is pointing towards basically, that we should go towards a clustering algorithm, and that it is better in this case because we have got all the intuition pointing towards that there is already some underlying structure and some clusters that we can form in the EDA itself. So how do we approach such a problem? So what do we do this that how do we do this? First of all, let me quickly explain to you how clustering works in general. Okay. So in clustering, basically clusters are made, and each of the clusters consist of some points. Okay. So imagine that there is a cluster one having these points. Okay. All of these points. Okay. And there is another cluster, cluster B or cluster 2, having these points. Okay. Now my goal is to basically separate them into two different blobs. Okay. So since I see that the green points are all concentrated here and the red points are all concentrated here, maybe I can just make a cluster around them. So this can be called as a cluster of points. Okay. And these ones can be called as a cluster of points. So now, how does this algorithm look like? How does it work like? So what happens is that, in the random feature space, whenever we do the EDA, this is what the EDA is for. We get some distribution of points. Basically, how our points are distributed in the feature space. So we saw it in the EDA as well for this specific problem, that the points are distributed like this. They can be easily put into clusters. So this is what the algorithm asks us to do. Now, how does the clustering work like? See, clustering has two goals. If I write it down, okay? Like if I write down the primary goal of clustering. Clustering's primary goal is to minimize the intra cluster distance and maximize inter cluster distance. Okay. Now, don't worry, I will quickly be explaining these. These are very easy. So, what does intra-cluster distance mean? Okay, what does intra-cluster distance mean? So, imagine that we are talking about this green cluster here. So, one very important thing, there is the center point in the clusters. Basically the point around which the whole cluster is formed. That point is called as the centroid of each cluster. Okay, so if you just look at the green cluster, this is the centroid of the cluster. Okay, if you look at the red one, this large red cross is the centroid of the cluster. It is basically the centermost point around which all of the other data points are based. Okay, now What is the intra-cluster distance? The intra-cluster distance is nothing but the distance of the centroid from all the other points in the data. Okay, so we have got this green cluster. Let's call this cluster 2 and cluster 1. Okay, so the distance of basically the points of the clusters inside, okay, these distances need to be minimized. Okay. The goal of clustering is to minimize these distances and maximize the inter-cluster distance. The inter-cluster distance means this distance, the distance of one cluster to another. We need to maximize this distance. Now, very important, very important. Why? Why do we minimize this and why do we maximize this? Why not the other way around? That's the first question. So it's pretty easy. See, clustering, the whole intuition of clustering is to bring similar points together, similar data together. So, the red points here are together in the first cluster, in cluster C1, because the red points are similar to each other. Okay, they have some similarity, they have some structure in them. The green points are similar to each other, which is why they are closer. So can I say if points are closer to each other, then naturally the distance between the points is going to be very less, right? Let's say that, if the points were very far away, let's say that there was the white point here, then there was another point here, here, and here. So could I make a cluster out of these 5 points? No, I cannot. It's just not possible. It would be a horrible cluster to make. I cannot fit them in one cluster. See, I'll have to do something like one cluster, and three clusters. And these are not the same points anymore because they are in different clusters. So it's like a naturally understandable thing that if we are talking about clustering, we want our points to be the same. If the points are same, then they can be accepted as the part of the same cluster. Okay. Now, let's say we have got this cluster made. Okay, fine. They have got similar points and the distances between points, which means the intra-cluster distance is minimum, which is why we were able to form the cluster. Similarly, we were able to make this red cluster. Now, is the red cluster and the green cluster same? No. How could it be the same? They are completely different clusters. Their red and green points are made them with different colors to show, to basically visualize that they represent completely different data points. They can never be together. They can never be close to each other. If they are close to each other, they would be part of a single cluster. Let me show this to you very quickly again. So let's say I've got again these red points right here. Okay, these red points in some large feature space. And then let's say I got, these green points. Just a second. These green points. Okay. So I got these green points here. Okay. These ones. Now, when you look closely, look at how close these points are to each other. Okay. It's not, we cannot say it clearly that the red points are different from the green points. They are in fact, very close to each other. So can I make a cluster here? Can I make two, three different clusters here? The answer is no. The answer here is that, we make only one cluster. Why? Because even though the red and green points look different, the distances between them are very, very less. See, these are very close to each other. These are very close to each other. These are very close to each other. I cannot assign them different clusters. That would be the wrong solution, which is why I assign them one cluster. So if you want different clusters, if different clusters are being made as part of the algorithm, it means that the data points are different. Okay. So let me go back to our problem here. So we have got cluster C2 and we have got cluster C1. They are separate because the points are separate, which means the distance between these two clusters is going to be a larger value, which is why we have the intuition of maximizing the inter-cluster distance. Okay. So the intra-cluster distance is the within cluster distance, the distance between points inside a single cluster, and the inter-cluster distance is the distance between two separate clusters. Okay. So we maximize this one right here, and we minimize these internal distances because we want the points to be closer together. We want the clusters to be compact. Okay, that means that the clusters are, eventually more accurate. That is the basic intuition, the basic goal of our clustering algorithm. Clear? Okay. Moving forward, no, it's not done yet. There is There's like good amount of stuff in here. Now, since we have like got the basic intuition, we still have to discuss the other stuff. So, our goal, if I write it again in a more formal way, like in the way we write a problem statement, maybe we can write that our goal is to find k clusters. Okay. Why k? Because usually in real world data, we cannot fit everything in one cluster. There are multiple clusters and they can be any number. So we just assign it a variable k. Okay. So find k clusters to minimize within cluster variance. Okay. So within cluster variance, again, it's not a new term. It basically means, uh, it basically means the variance between the distances inside the cluster. So it is similar to the intra-cluster distance that we just discussed. So we need to minimize that variance. Now, every machine learning algorithm that we have been, doing till now, it has a problem statement. Okay. So we are done with the problem statement. We have understood this. What about the loss function? Okay, like you understand this intuitively, but what are we doing mathematically here in order to do whatever we are aiming to do in order to minimize the intra-cluster distance and maximize the inter-cluster distance? What is the problem that we are solving? So let me write the objective function for this, okay, and then I'll explain it. So if I write the objective function as j, okay, it can be anything. It's written as j, okay. It's like summation k summation xi belongs to, it's a little big, belongs to ck xi minus mu k whole squared. Okay. Don't get overwhelmed looking at this. It's very easy. I'll explain it just in a second. So what does this mean? So guys, this is nothing but, this xi minus mu k whole squared is nothing but the Euclidean distance. Okay. For those who have not heard about the Euclidean distance, I'll quickly tell you it's basically a way how we get distances between points in the feature space. There are other distances as well, but the Euclidean is one of the most intuitive ways to do it. Okay, so this is nothing but the Euclidean distance. Okay, Euclidean distance. And it's the Euclidean distance between xi and mu k. What are xi and mu k? Xi are nothing but points inside cluster. Okay, which means the all of the points inside any particular cluster. And mu k is nothing but the centroid of the cluster that we are dealing with. So, the centroid of cluster K. Okay. So basically the distances that we calculate of the individual points from the cluster, these are the distances that we are talking about. Okay. Uh, Let me quickly get back with this. Okay. Yeah. Okay, so this is what we are calculating. Now, very important thing. These are two summation signs in here. Don't get confused because this summation sign is basically for the Euclidean distance formula, and this summation sign is basically, applying this formula for all the clusters. Okay, I'll explain this. I'll open it up apart even more, but just currently understand that this is calculating the distance between the individual points in the clusters, and this is basically saying that do this for all the k clusters that we have on our hands. Okay. And this is the function we are aiming to minimize. Why? Because this is the loss function. Okay. The loss function for this algorithm. Now, how is it reduced? So to reduce this function, we use something called as the Lloyd algorithm. Okay. So the Lloyd algorithm, it's just a name of an algorithm. No need to memorize this. You can just understand it intuitively so that whenever you're using it in the future, it becomes easier for you to, understand these things. Okay. So, uh, so the Lloyd algorithm, if I open it up for you, It is an optimization algorithm which aims to reduce this function right here. How does it do it? It does that in two steps. First of all, the Lloyd algorithm is saying that, whenever we are assigning clusters, okay, I am going to take the minimum value so that my point gets inside the nearest cluster. What does this mean? Okay, what does this mean? I'll tell you. So first of all, this argmin value. So argmin basically means that we calculate these distances, and whatever is the minimum value for these distances, we take that. Now take that where? Take that where? This is very important. So like I said, in the feature space, we do not have pre-built clusters. So let me go back to this picture here, okay, that we took from the EDA. So, let's assume that I do not have any of these clusters in here, okay? I am running the algorithm for the first time. So what's going to happen is that, I am, let's assume, going to take this point and maybe this point, then this point. So individually, I'm going to take all points and I'm going to calculate distances between the points. So I'm going to calculate the distance here. Okay, I'm going to calculate the distance here. Then the distance between these two, then these two, and I'm going to do this for all the clusters. Okay, for all the points one by one. Now the points which are closer to each other will be allowed in a cluster. So, you can see that these points are very far from each other, right? These are also pretty far from each other. These points are so close, these points are very close. So these points which are close to each other will naturally be clustered together. So when we find out the distances, we assign the point with the minimum distance to that specific cluster. Okay, so this is what this value is doing right here, the value that we had right now in the Lloyd algorithm, Nostality. So this value, this is calculating the Euclidean distances. Oh, sorry, it's the eraser. Okay, so this is doing nothing but calculating the Euclidean distances, which means the distances between each points. And then it is saying that, whenever you do that, take the minimum value out of all of that and assign it to that cluster. Okay, so there are already many clusters lying around. We are saying that, whichever cluster centroid has the minimum value, you give it to that cluster. Okay, so that is the first step of the Lloyd algorithm. The next step is another part of our optimization, in that, basically what we are doing is we have to recalculate the centroid of each cluster. Okay, I'll tell you how it is being done. So it works by applying this formula. Mu k is equal to 1 upon mod of ck summation xi belongs to ck xi. Okay. Again, no need to worry about all of these formulas. You don't need to memorize them, but they are important for a good understanding about the model. So now we tell you what's happening here. Okay. So I will take an example. Let's say I've got these points in here. Okay, white points specifically. Okay, all points I'm making them as white because originally this is something like our feature space is going to look like. Okay, let's say this is what our feature space is looking like. Okay, basically our scatter plot that we are going to make for any problem. It can be anywhere, anytime. Okay, let's say this is our feature space. Now, how do we approach a clustering problem? First of all, the number of clusters we have in the beginning is zero. Okay, there are no clusters right now because it is the beginning of the algorithm. So how do we initialize the algorithm? We initialize the algorithm by calculating the distances. The distance is where? Now that is the bigger part here. The distance calculation, since it's just a mathematical value, it is not all that computationally heavy, but it does take time because we have to do it for all the points. Okay, so let's say we start at this corner right here. So we calculate the distance from here to here, this, then from this, then from this. Now we can already see that these points are already clustered together. So, once we have calculated the distance for all of them, we can maybe already create a small cluster here and we can say that this is our centroid of the cluster. Okay. So now our centroid has become one, which means that, we have one cluster. Okay. We'll update it later, but we have got one cluster now. Now what's going to happen again? We are going to go to this new point here. Again, this distance will be calculated. This will be calculated. This will be calculated. And these distances will also be calculated. These ones. Okay. Now, when we calculate these distances, let me change the color to show this to you. Okay. So when we calculate these distances, we can already see that they are very large values. Okay. Because these values are closer together. So this way we can infer that none of these points will go inside this cluster. Okay. We will have to form some separate cluster of these points because they are completely different from the above one in white. Okay. This is how we decide that, which point should go to which cluster. Because, we already had this white cluster here. And let's say that I'm at this point right here, this point. And I try and calculate that, maybe it can go to this above cluster. Maybe it can go to the cluster below. How should I do it? This is how I do it. I calculate the distance of this from this one, this one, this one, and I calculate it from this one. I can already see that this distance is going to be bigger, which is why this point needs to be assigned to a different cluster. Okay. This way, this algorithm will be recomputed every time until all the points are covered. Okay. So in its working, it's a pretty lengthy algorithm. Okay. And whenever new points are added to the cluster, the centroid has to be recalculated. So for that, I'll show you like a separate example. Let's say that we have these points. Now, like I said, distances are calculated one by one. Okay, which means it takes a bit of time to calculate the distance. So let's say that these distances that we have on our hands. Let's say this distance is calculated first. Okay, fine. Then this is calculated, fine. This is calculated, fine. This is calculated. Now let's say at this point where we have about 5 points, the model feels confident that yeah, five is enough, and maybe we group together to form a cluster. We can, right? Yeah, and we say that this is our centroid. Okay, that's fine. But later, the model calculates more distances. Now it's like, this point is also closer. Okay. This point is also closer. This point is also closer. This is also closer. So all of these 3 points and these points as well, they have to be added to our cluster. Now, when we add new points to our cluster, our centroid changes. Why? Why? Because the boundaries are changing now. The centroid is supposed to be the center point in the cluster. Okay, approximately. So when the boundaries are changing, when the cluster is becoming bigger, the center is also going to change because, let's say that in the end, I get my final centroid, I get my final cluster as this. Now, does the green circle and the red circle have the same center? No, the green center will probably lie around somewhere here, and the whites lie in somewhere here. So the center has changed, which is why we have this centroid update step that we just had. This step right here in the Lloyd algorithm. So in this step, that is exactly what we are doing. Once we have assigned, okay, this is called as the assignment step. So once we have assigned the new points to a cluster, we need to recalculate or recompute the cluster centroid or the cluster mean. Why? Because it has changed. Okay. This is very important. This is the only part in the entire algorithm to understand. Rest of it is like super easy. Okay. So this is how the Lloyd algorithm works like, and this is why it is very important to do this. Okay. One thing that I forgot to mention, it's a small mistake on my part. You know how I mentioned in here that we need to minimize the within cluster variance. Okay. So this within cluster variance has an official name. Okay. Within cluster variance, this has an official name and it's nothing but just a name. It is called as inertia or distortion. Okay. It's just like a name. You can use it later. It's called as inertia or distortion. So you can also say formally that, we are trying to minimize the inertia for all the points. Okay. For by using the clustering algorithm. Okay. So we have got the algorithm, the intuition, and whatever math is involved. It's pretty basic. Now comes a very important question. Let me quickly go back to the repo. Okay, to show this to you. So this is the objective function that we are reducing. You can read it. This is the optimization. This is the geometric assumption. Basically, I stated this in the beginning that we assume our clusters to be spherical because Euclidean distance defines distances inside a circle very well. So this makes our job very easy. If they are weird shaped, crescent shaped or something, it becomes a bit difficult to move forward. Okay. And then we basically go on to a different clustering algorithm, not the k-means algorithm. Okay. Complexity, obviously, we'll deal with it later. Now, yeah, comes the main thing. What's the number of clusters that we start with? Or what is the number of clusters that, we initialize or basically what is the number of clusters we end up with? Because we can intuitively go around doing what we did in the notes, okay, but the thing is in real life there are a lot more points, so obviously I cannot take a pen and paper and draw out clusters myself because the algorithm is doing it for me. Why should I do it? It's a simple thing. So the thing is, what should we initialize the algorithm with, or what value of the number of clusters k, it is represented by k, should we take? So this is where the very important part comes in, which is the selection of the value of k. First of all, understand as to why this matters. So, the k value matters because it is basically deciding how many clusters we are getting. And it should be based on the data. But, if we just try to randomly guess its value, any one of these two cases can happen, which are mentioned in the table. So if the case too small, it will be the case of under segmentation, which means like under representation. Okay, the model is like too simple. There is an underfitting risk. The model does not, really understand the real patterns which are lying in the data, which we were tasked to find. But we did not find it because we took a k value which is too small. Okay. Centroid's position won't be wrong. The centroid should be far from each other. If the k is too large, it will lead to over segmentation, which means sort of like an overfitting case. Noise will appear, and basically the clustering algorithm will start learning from the noise as well. Okay. And interpretability won't be as clear, and the model will ultimately become unstable. Okay. This is simple. This is why the k value becomes very important. Okay. Now, the methods for selecting optimal k. Now, I have discussed basically five methods. Usually, the top three methods that I am going to discuss are like very intuitive. Everyone discusses them, but I have discussed two more methods. They are also simple. So quickly, let's go on to that. So the first method to find the value of k or select the value of k is called as the empirical method. Oh, sorry. Yeah, let's choose this one. Okay. Yeah, sorry for the delay. So, the first one is called as the empirical method. So the empirical method is nothing, it's just a mathematical formula. Okay. So it says that, assign k as under root n by 2, where n is nothing but the number of samples in the data set. Okay. This is very naive and it is wrong most of the times, but it is chosen sometimes as the baseline value. So maybe you can go forward with it in the baseline. Okay. But this is like very primitive. This is not used now in any pipelines. Okay. So after the empirical method, the second method that we get is a good method, but it is still pretty primitive. We get the elbow method. The elbow method. So the elbow method is explained in a lot of places. The elbow method basically plots, it's like a graph. Okay, it's better understandable in a graph. I'll show it to you. So the elbow method basically, plots for us. We show it to you. Yeah. Yeah. So the elbow method basically plots the inertia values with the number of k. Okay, so what happens is, let me copy this to show it to you. So copy image and let me go there, paste. Okay. So, guys, our goal in the algorithm, as we discussed before, is to, minimize the inertia or, minimize the within cluster variance. So, if we try to plot inertia with the number of clusters k, okay, like we have done here, we will see that as the number of clusters increase, the inertia decreases. Okay, that is typical because inertia wants to, inertia is saying that I want to minimize the within cluster variance, and as the clusters are increased, the variance between clusters themselves are going to reduce a lot. Okay, so when we plot the graph between the inertia and the number of clusters, we can see that it is declining sharply. Okay, it is declining sharply in the beginning like this, then it is going here, then it is going here. But we see a point in a graph where the number of clusters have increased from 2, 3, 4, and then the values have suddenly declined. So the point of the steepest decline is called as the elbow point. Okay, like the elbow is a sharp thing, right? Which is why this is called as the elbow method. So we can see at this point, the value of inertia has suddenly declined with increase in K. Okay, it has declined at this point as well. But the thing is, at this point, the number of clusters is just three. Three is not considered a good value to take because, it's considered that the algorithm has just started working. Let the algorithm work its magic. Take the values which come at a later stage, which is why we do not select this or this because, it is like very easy to answer that the value is sharply declining here and it is sharply declining here as well. So why do we take this value here? Because, some iterations have passed by. The model has been allowed to train. Here it is just beginning its training in these phases, which is why the value of k is equals to 5 is selected from here. And the intuition is very simple. The intuition is that, we want to minimize the inertia. Okay. And this is showing us where the inertia will be minimized when the k value is 5. Okay. So we are basically doing like an inertia versus k, and wherever the inertia is the minimum or wherever the inertia has a sharp decline after the first few iterations, that k value is what we pick. This is the elbow method. Okay. It is okay. It has its disadvantages, but it is still selected a lot. Okay. You can read this as well. So there is a large drop early, which is fine, which is why we do not consider this. We only consider the drop which comes later, like we did here. Okay. The weakness is that the elbow method is too subjective. It is not model specific as well. So for the third one, we have got the silhouette score. This is a better model to, choose to select the value of k. So if I write here silhouette score, so silhouette score is more intuitive to understand. Okay, silhouette score, if I write S of I is equals to B of I minus A of I divided by maximum value between AI and BI, whatever is the maximum. Okay, this is the formula that is running behind. Now, quickly, what do these things mean? So, A of I is nothing but, the distance of I to all points inside cluster. Okay. So basically, we take any point I and we find the distance of that point I inside all of the points in the cluster. That is called as the AI. Okay. And this is formally called as cohesion. Okay. It is like the definition for cohesion. Okay. What does BI calculate? BI calculates the distance of I to all points in another nearest cluster. Okay. So I'll show this to you what it means visually, but just try to absorb this right now. And this BI distance is formally called as separation. Okay, separation value. So if I try to show it to you, let's say that we have got We have got maybe like a cluster A in here and a cluster B in this case. Okay. And we have got different data points in this, like this. And we have got different data points in here as well. Okay. So now our what we are saying is we need to calculate AI and BI. So these values, the average of all of this inside any cluster, these are called as the AI values, A of I for any one cluster. So the A of I value will be calculated for this cluster and the A of I will be calculated for this cluster. So you know this formula for the Silhouette score, this is calculated cluster wise. Okay. Then what we do is we calculate this distance, the distance between any point in cluster A to the points in cluster B, this distance, and we add them up. Okay, which is why you know we have written I here. I here means that this is a single point, and we do this for all the points, and we average it out. Okay, so the Silhouette score also, you know, tells us like a very, gives us a very intuitive idea, and its range basically lies between -1 and 1. 1 is considered the best value, meaning that whenever you calculate S as the Silhouette score, you should aim to get a higher value, a value which is closer to 1. If it is closer to 1, then whatever K value you have selected, it is good to select. Okay. 1 means that basically our clustering is correct. The point is well in the inside the cluster. It is in the ideal position. 0 means it's a boundary point. It lies between two clusters, and -1 means that there is a wrong clustering process being done here. Okay. So this is how the curve of Silhouette scores look like. So again, we can see value around 5 is giving us the maximum value of the Silhouette score. So maybe we can select 5. Okay. Now, these two, I have introduced two more of them. They are not necessary, but you are very welcome to read through them. It's the DB index and the CH score. So they also give us a very intuitive idea. So, you know, the Davis Bouldin index, it basically gives us an idea about, you know, the worst case similarity between each cluster and its most similar neighbor. So, you know, we have got two clusters in here. Now, Si and Sj are the average distances from any cluster I to its centroid. Now, let me show this to you in the form of an example very quickly. So, you know, we'll take the similar example because it's pretty easy to understand. So we have got, you know, again, cluster A and cluster B, or cluster 1 and cluster 2, whatever. Okay. So just so, you know, in this case, what is happening is that we are calculating Si and Sj, which is a similarity. Okay. And then we are calculating Mij, which is basically the distance between the centroids of the two clusters. This is centroid 1. This is centroid 2. This distance is Mij. Okay. This Mij we are calculating. And Sij is basically the average intra-cluster distance, and Sj is basically the average inter-cluster distance for the second cluster. Okay. So if you look here, S is the average distance from points of I to centroid of Ui. So, you know, like the distances between points, this point and the centroid, this point and the centroid, and so on. And then we average all of them out. Similarly for this one, this distance, this distance, this distance, and we average them all out. Okay. So it is basically like a very good representation covering both the intercluster and the intra-cluster distance. Okay. So as we mentioned before, this distance, the distance between the two centroids, need to be maximized because the two centroids are supposed to be different from each other. And this Si and Sj, which is basically, you know, the average of similarity, they need to be minimized because the points inside any particular cluster are similar to each other. So overall, this score needs to be a lower value. Why? Because if this is higher, then this whole value will be lower. Because, you know, Mij is in the denominator, it is dividing. Okay. So always aim for a lower value of the DB curve or the DB index. Okay. So again, to plot this, it's very intuitive. We see we get at k is equals to 5, we get the minimum DB curve. So this is the third time we are getting 5. So maybe 5 is the answer for the number of clusters. Okay. This is the CH score. Okay, it gives us the ratio. It's like a ratio criteria. This is a bit too convoluted to understand, but it is basically the ratio between within cluster dispersion and between cluster dispersion. So it is saying that, this value, if you look at right here within cluster dispersion, this we do calculate as part of the Lloyd algorithm itself. This is nothing but like the within cluster variance, which we wanted to minimize. So we can say that this W value is what we try to minimize, which is why we should aim for a higher CH value curve. Okay. A higher CH value curve means that the model is stronger. Okay. So again, we can see values above 5. Okay, 10 or I think this 9 or 8 value has given us the highest CH score. Okay. And the CH score gives us a very good ratio, a very interpretable ratio. So these were the two new points I wanted to introduce. Okay. So this is how you can calculate it. This is a neat trick I tried to implement. It did work. So, we cannot really implement grid search CV here because this is an unsupervised algorithm. But what I did was I said I gave values to grid search CV and I said that whatever gives us the highest silhouette score, take that value of K. So this is another trick to get the value of K. Okay. But the first five, they are really the key values which we should be using. Okay. These are the metrics. So, the values that we calculated, the Davis Bouldin score and the Calinski Harabasz score, the CH score, they work as, the metric values as well. We use them to calculate which is the best K, but they work to calculate whether the cluster quality is good as well. Okay. So these are some of the metrics. Inertia, we already did it. Silhouette score, we discussed. And we also take into account the average intra-cluster distance, which need to be minimized because that leads to the formation of tighter clusters, which we are eventually after. Okay. So this is a beautiful table comparing everything. So what we did was I'll show it to you in the code. What I did was I basically took all of the methods and compared them throughout. So, these are all the six methods. We took all of them and we used all of the methods to find K and we found K from all of them. So 5 is the majority value here. Okay. 5 is the majority value here. So eventually the answer does become 5. But the point here basically is that, since there is no true label to compare from, we can never really point at a particular value in the k-means algorithm. Okay. We have to do like a good analysis in order to get an idea as to what is the correct value of k. Because, different things are giving us different answers. Silhouette score is maximizing the inertia. See, the inertia here is maximum, but actually we need to minimize the inertia. Okay, the empirical is minimizing the inertia the most, but the empirical does not have a very high silhouette value. Okay, it has the highest, it has the second highest Calinski Harabasz index. So you see, the methods are failing in some places and they're good in some places. So this is why an in-depth analysis in selecting K is very important. Okay. Then we go on to the cluster visualization. Okay, so what I have done is that using all of the different methods that we just discussed, I've plotted out the clusters. So this is how the empirical method tries to make 10 clusters, and the crosses represent the centroids. Okay, this is for the silhouette; it makes only 5. This is for the Davis Bouldin and the Calency Harbas. Okay, you can look at them later. Now let me quickly get back to the code to show you how we have done this. So for this, we can run this for loop. This basically calculates all of the values together. This was the stuff we did. Okay, after scaling. These are the labels. Silhouette score. This is selecting the values of K. We took 6 methods in total. The grid search CV I have counted it as a method here. Okay. You can import all of this here. This is all the lists that we made right here. This is we made separate lists in order to have the values of K to the grid search CV. Okay. Then we print all of these values separately right here. Then we print the methods to get the table. And finally, the model training time, inference latency, the usual stuff. And then, we calculate the intra-cluster and inter-cluster distances because we needed to make the visualizations. For that, we need it. Okay. Then the visualization and the tables. So you can see this visualizations here. This is the results that I just wrote in the repo. Okay. These are all the visualizations that we got. And the table that we implemented. Okay. These are the curve values. This is basically used to select the value of K. Okay, very intuitive. Now, Very important. Let's quickly go through the time complexity. So the time complexity here is not that much because, like I said, these distance calculations do not take a lot of computation power. So, it is basically INKD. So, I is the number of iterations until convergence. It is not that high because in practice, clustering is a pretty quick algorithm. So, it around 10-15 iterations you will probably converge for even for medium to large data sets. If it is too high, it might go higher, but 10-15 is the usual answer for I. N is the number of samples, okay? K is the number of clusters formed. So let's say that 5 was the number of clusters and D is the features, okay? This is a pretty quick algorithm because it does not scale to quadratic values. This value will still come out to be like a linear value and it will be very fast to run during inference as well. Okay. Space complexity, we need to store all of the centroid values and the entire data at least once, which is why this is the space complexity. So for D different features, we have got K centroids for K clusters, and N into D is basically a table size. Okay. Storage does require a value, especially if N is high, but centroids are like 5 or maybe 10. They are negligible compared to the D and N values here. Okay. This we discussed. Let me quickly get to the failure cases. Basically, this model has run well. It has given us very good interpretable results and a very good analysis. But we need to understand what are some places where K might fail, or this K means clustering might fail. So the first one is the problem of, clusters which are not spherical shape. Basically, I discussed that when we get star shaped or crescent shaped kind of clusters, we do not we cannot intuitively go for an algorithm such as k-means because it assumes convex and spherical clusters. If these clusters are absent, we cannot really get a final result, and that causes an issue. So in those cases, we need to think of maybe a different clustering like a Davies scan or something else. Okay. If the cluster density is varying, basically, k-means tries to assign each cluster using the Euclidean distance that we just calculated. So, like a sparse cluster very far away from the centroid will lose points to a cluster which is denser but closer. So, basically, like, denser clusters dominate in this case and the sparse ones are ignored. So, this is also a case where the model might not give results which are that interpretable. Okay. This is very important that sometimes the initialization is poor because the objective is non-convex, which means that we can find a local minima value. Different centroids can give different final configurations. Okay, so this is also an issue. Outlier problem always stays down. You can read the rest as well. The most important was the problem of non-convex clusters because if non-convex clusters are there, we have to stray away from the k-means algorithm and go for something else. So that is the most important one. Okay. This is important. This is also a good point. Basically it says that if the k values that we just chose are only chosen by the geometric metrics, rather than, taking into account all of the commercial segments, then maybe we won't get as profitable results because we are eventually doing all this for business optimizations. Okay. You can read this. These two were the new things basically to learn here. Others you might find everywhere. The Calinski Harabasz score and the Davies Bouldin the index. Okay. This is new stuff to learn from. Rest, I think we have already covered everything. Okay. You can read the repo. It has got similar explanation. It is very intuitive to understand. Okay, and this is the entire code for it. Very intuitively written. You can use it. Okay. So I think with that, this is a wrap for day 11. Let me quickly go back and check what problem we have for tomorrow. So what do we have for day 12? For day 12, we have a dimensionality reduction problem using PC. Very interesting. Thank you, and I will see you tomorrow.